Chapter 10, Hypothesis Tests. And this is regarding a parameter. So we're getting into one of the most powerful statistical tests, and that is the hypothesis test. And in this chapter, we will do the first three sections. All right, so 10.1, the language of hypothesis testing. So it's actually a very formal process in statistics. There are certain ways a hypothesis test must be carried out and conducted. And it turns out that the results of a hypothesis test are, when they are conclusive, they are as good as a matter of fact. Um, they will hold up in the court of law, hypothesis tests, and things of that sort. So there are three objectives in this section. Determine the null and alternative hypothesis. Explain a type 1 and type 2 errors. And then also state conclusions to hypothesis tests. So here we have a question here. And this could be a hypothesis, Is your friend cheating? So it says a friend of yours wants to play a simple coin flipping game. If the coin comes up heads, you win. If it comes up tails, your friend wins. Suppose the outcome of 5 plays of the game is true, or tails, 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 tails. Is your friend cheating? So we have a little sample space of 5. They're all supposed to be independent. Are these results enough to conclude that maybe that your friend is flipping some kind of biased coin, or how he flips the coin? There's some kind of um, bias in it, or maybe it's not as random as it's being flipped. We don't know, but this is really the job of a hypothesis test. Using a hypothesis test, you can actually determine with a very high degree of certainty if your friend is cheating or not. So hypothesis tests can be used to catch people in a lie, right? So we'll determine the probability of getting 5 tails in a row, assuming that the coin is fair. The flips of the coin are independent, so the probability of 5 tails in a row would be written like this, which would be 2 times 2 times 2 times 2 times 2, okay? 1 over 32, which is equal to 0.03125. That's about 3%. All right, it's pretty rare. Anything under 5% or 0.05 is unlikely to happen. Now, the theoretical probability of this happening, it would only happen, we would expect about 3 out of 100 times. So it can happen. It did happen. But how rare is it? There's one way to interpret this. If we were to flip the coin 5 times, 100 different times, right? Or sometimes you could just flip 5 coins all at once and see. But in this case, it was 1 coin being flipped 5 times. And if we were to do this 100 times, we'd expect about 3, right? So you can make 1 or 2 conclusions, all right? Your friend is not cheating and happens to be lucky. Your friend is not using a fair coin. Now, is your friend cheating, or did you just happen to experience an unusual result from a fair coin? This is the heart of a hypothesis testing there. We make an assumption about reality, and we then look at sample evidence to determine whether it contradicts our assumption. So determining the null and the alternative hypothesis. A hypothesis is a statement regarding the characteristic of one or more populations. In this chapter, we look at hypothesis regarding a single population parameter. Hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. Here are some of the steps. Number one, make a statement regarding the nature of the population. Collect evidence or sample data to test the statement. 3. Analyze the data to assess the plausibility of the statement. Excuse me. The null hypothesis, denoted H sub 0 or H naught or H null, is a statement to be tested. The null hypothesis is a statement of no change or no effect or no difference, and it is assumed true until evidence indicates otherwise. The alternative hypothesis is denoted as H1. Sometimes you may see H sub A, little a, which stands for the alternative. But in this case, it's H1. And this is a statement that we are trying to find evidence to support. So in this chapter, there are 3 ways to set up the null and the alternative hypothesis. Number 1, the equal hypothesis versus the not equal hypothesis. So would be a two-tailed test. All right. Where we have the parameters equal to some value, and then the alternative is that the parameter is not equal to that value. The left-tailed test, this is where, again, the null is equal to some value, and that's always going to be the case. The null hypothesis must always be set to some value, and then the alternative, what we're trying to prove true, to reject the null. In this case, that the parameter is less than some value, and that would be a left-tailed test. And then the other case, the third case, is when we have the alternative greater, the parameter of the alternative is greater than some value. That would be our right-tailed test. So the null hypothesis is a statement of status quo, or no difference, and always contains a statement of equality. The null hypothesis is assumed to be true until we have evidence to the contrary. We seek evidence to support the statement and the alternative hypothesis. Left and right-tailed tests are referred to as a one-tailed test. It's either the left or right tail, which is just that one tail. Notice that whether it's less than will be left, if it's greater than, it's going to be right. And then also, let's go back. In all 3 tests, the null hypothesis contains the statement of equality. When the alternative is not equal to, that's two-tailed. So determine the null and alternative hypothesis, and then state whether the test is two-tailed, left-tailed, or right-tailed. So here's the situation. It says the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the Food and Drug Administration wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. All right. So we have the hypothesis deals with the population proportion P. So if the new drug is no different from the competing drugs, the proportion of the individuals taking it who experiences a headache will be 0.02. This is the statement of no effect. We want to determine if the proportion of individuals who experience a headache is more than 0.02. This is a statement we're attempting to find evidence to support. So the null would be H null would be P equal to 0.02, and the alternative would be that P is greater than 0.02. Okay, so this would be a right-tailed test as well. We see that it's a right-tailed test because we're um, setting the alternative to be greater than. So on the right side of the population proportion. The Blue Book price of a used 3-year-old Chevy Corvette Z06 is $59,000. Grant wonders if the mean price of a used 3-year-old Chevy Corvette Z06 in Miami metropolitan area is different from 59,083. All right, so the hypothesis deals with the population mean. And so we're going to set the mean to be 59,883, and the alternative is going to be not equal to. We don't know if it's going to be more or less. We're just going to set it to not equal. And in which case this would then be a two-tailed test. And here's another question. The standard deviation of contents in a 64-ounce bottle of detergent using an old filling machine is 0.23 ounce. The manufacturer wants to know if a new filling machine has less variability. That's less variability. All right. All right, and this is how we would set it up. Notice the population proportion is, it's not P this time, it is little sigma, it's the population deviation. All right, we're going to look into explain type 1 and type 2 errors now. So there's basically 4 outcomes from hypothesis testing. Number 1, you can reject the null hypothesis when the alternative hypothesis is true. This decision would be correct. Number 2, we could do not reject the null hypothesis when the null hypothesis is true. This decision would be correct. 3, reject the null hypothesis when the null hypothesis is true. This decision would be incorrect. This type of error is called a type 1 error. And then 4, do not reject the null hypothesis when the alternative hypothesis is true. This decision would be incorrect. This type of error is called a type 2 error. Okay. It could happen. And also, a lot of it depends on the sample of evidence that we collect. You know, it could be a very rare case. There could be outliers. It could be tainted. Um, the test could have been, there could have been mistakes in the calculations that resulted in the wrong outcome. There's a nice little table, and this table can be used to understand the errors there. So it's kind of a two-way table. Like, we can look at all 4 different cases. When H null is true, we do not reject or we reject. When H1 is true, not reject or reject. So it's kind of a helpful little mechanism to help remember the type 1 and type 2 errors. So here we have a problem, and the researcher conducts a hypothesis test with H null P equals 0.02 and the alternative P is greater than 0.02. A type 1 error is made if the sample evidence leads the researcher to believe that P is greater than 0.02. We reject the null hypothesis when in fact the proportion of children who experience a headache is not greater than 0.02. Explain what it would mean to make a type 2 error. Well, the type 2 error would be made if the researcher does not reject the null, that the proportion of children who experience a headache is actually equal to 0.02, when in fact the proportion of children who experience a headache is more than 0.02. In other words, the sample evidence led the researcher to believe that P equals 0.02 is equal to that, when in actuality it's actually larger. So the probability of making a type 1 or type 2 error is denoted by alpha and then also beta. The level of significance alpha is the probability of making a type 1 error. As the probability of type 1 error increases, the probability of a type 2 error decreases, and vice versa. And now finally, state conclusions to hypothesis tests. Caution. We never accept the null hypothesis because without having access to the entire population, we don't know the exact value of the parameters stated in the null hypothesis. Rather, we say we do not reject the null hypothesis. All right. This is just like the court system. We never declare a defendant innocent, but rather we say the defendant is not guilty. It's a very technical type of thing, and it's very logical as well. So we have this problem again at Medco Pharmaceutical Company. They've just developed a new antibiotic. 2% of the children taking competing antibiotics experience a headache as a side effect. A researcher for the FDA believes that the proportion of children taking the new antibiotic who experiences a headache as a side effect is more than 0.02. So from a previous example, we know that the null is P equals 0.02, and the alternative is P is greater than 0.02. Suppose that the sample evidence indicates that the null hypothesis is rejected. State the conclusion. So the statement in the alternative hypothesis is that the proportion of children taking the new antibiotic who experiences a headache as a side effect is more than 0.02. Because the null hypothesis is rejected, there is sufficient evidence to conclude that the proportion of children who experience a headache as a side effect is more than 0.02. Suppose that the sample evidence indicates that the null hypothesis is not rejected. State the conclusion. So it seems pretty straightforward here. We have, because the null hypothesis is not rejected, there is not sufficient evidence to say that the proportion of children who experience a headache has a side effect more than 2. It's as simple as that. Section 10.2, hypothesis tests for a population proportion. So in this section, we really cover how to really do an entire hypothesis test. So let's dig in. The politician hires a polling firm to obtain a random sample of 1,000 registered voters in her district and finds that 534 are in favor of the policy. So p hat equals 534 of 1,000, or that's equates to 0.534. Do these results suggest that among all registered voters, more than 50% favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is 0.5, and we just happen to survey a majority in favor of the policy? So in other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? All right, so we really need to understand this. Let's move on. When observed results are unlikely under the assumption that the null hypothesis is true, we say the result is statistically significant and we reject the null hypothesis. So to determine if a sample proportion of 0.534 is statistically significant, we build a probability model. And so again, since the sample data are from an SRS and n times p times 1 minus p is greater than 10, and the sample size is over 1,000, is sufficiently smaller than the population size, we can use a normal model to describe the variability of p hat. The mean of the distribution of p hat is mu p hat, which is 0.5, and the standard deviation of the distribution would be given in this formula, which would be 0.016. So now we can calculate any probabilities that we want. Sampling distribution of the sample proportion for the politician example. So the logic of the classical approach. So we may consider the sample evidence to be statistically significant if the sample proportion is too many standard deviations. And we usually say about 2 deviations above or below the mean. Here, we're converting the z-score since we're able to model the normal shape based on these proportions. We can convert it. We would get 2.15. That is 2 deviations above the mean, the null mean that we suggested, that we assumed to be true. Therefore, we could say this is statistically significant. The results of our evidence of our sample is more than 2 deviations above the mean. We also call this the critical region, and the proportion of getting into the critical region is less than like 5%. In this case, it's about 2%. That's statistically significant. All right, so that kind of leads us into the p-value method, where you can compare the p-value with the alpha value. So we can compute the probability of obtaining a sample proportion of 0.534 or higher from a population whose proportion is 0.5 using the normal model. This is what we get. And the 0.0158 is called the p-value. And we will compare the p-value with the alpha. So that's kind of the way it works. The lower the p-value, that will suggest more evidence to reject the null. Yeah, so the first normal curve is based on the null, and then if we build a normal distribution based on our collected evidence, we can see now that, how statistically significant our results really are. All right, so we're going to get into the test hypothesis about a population proportion. And this is how you would conduct it. The first step is to determine the null and alternative hypothesis. Select a level of significance, we call it alpha. Usually 0.05 or 0.01 is a good alpha level. We have to check that our sample is obtained from an SRS, and also that n times p times 1 minus p is greater than 10. The sample values are independent of each other. And then we calculate the test statistic. Now, based on our test statistic, that's going to let us know what the p-value is. The p-value is that area, the proportion, or the probability of getting a number in that range. So in this case, they're just comparing the critical value with the test statistic. So if the test statistic is greater or less than, or basically if the test statistic falls in the critical region, that means it exceeds it to the right or it's lower to the left, and therefore we will reject the null. Basically means our sample evidence is statistically significant. All right, so technology will calculate the hypothesis test for us. Both StatCrunch and the TI-84s work. So here's an example. Humira is a medication used to treat rheumatoid arthritis, or we call it RA. In clinical trials of Humira, 705 subjects diagnosed with RA were administered 40 milligrams of Humira every other week. Of the 705 subjects, 66 reported nausea as a side effect. It is known that the proportion of RA subjects in similar studies receiving a placebo who report nausea as a side effect is 0.08. Does the sample evidence represent significant evidence that a higher proportion of subjects receiving Humira experiences nausea as a side effect than those taking the placebo? And we'll use an alpha level of 0.05. So first, we do have to state the null hypothesis, and it is that the population is 0.08 and the alternative is greater than 0.08. All right, the conditions are met. Our sample proportion is 0.09, and then we calculate our test statistic. Well, our test statistic did not go in the critical region. It doesn't exceed 1.654. Since we're using alpha of 0.05, that lets us know what our critical region is. So that critical region is 5%. It's the top 5%. 1.645 z-score separates the top 5% from the bottom 95. All right. So we get our results this way. So everything is correct. We set up the right tail tests. Here's another case. All right, so we're just going to kind of quickly go through this. We get our proportion, we calculate our test statistic, we compare it to alpha, or we can use the p-value method, get the p-value and compare that. Make sure the p-value is lower than the critical region area, lower than 5% or whatever it is. All right. So StatCrunch will also conduct a hypothesis test. It gives us all the good information, our proportion, our sample, our test statistic, and the p-value. Now, the two-tail hypothesis testing using confidence intervals. Let's look at this third objective, testing hypothesis about a population proportion using the binomial probability distribution. So it says, according to the USDA, 48.9% of males aged 20 to 39 consume the recommended daily requirement of calcium. After an aggressive Got Milk advertising campaign, the USDA conducts a survey of 35 randomly selected males aged 20 to 39 and finds that 21 of them consume the recommended daily allowance, RDA, of calcium at the alpha 10% level of significance. Is there evidence to conclude that the percentage of males aged 20 to 39 who consume RDA of calcium has increased? Well, we assume that it's 4.489, and we're going to look at our sample evidence of 0.6, and we're going to just compare how significant is 0.6. Is it a normal? And what we're going to do is calculate so we have 21 over 35 . So we're basically going to calculate the probability of getting x greater than 21. And in order to do 21, we subtract the area to the left, all the probability values to the left. All right. So that 1 minus binomial CDF. Keep in mind, binomial CDF counts from 20 all the way down to 0. And if we subtract that, we get the other case. Section 10.3, hypothesis tests for a population mean. And there are only 2 learning objectives here. Test a hypothesis test about a mean. And then number 2, understand the difference between statistical significance and practical significance. All right, so test an hypothesis regarding the population mean. Here it is. There are a few bullets. So testing regarding the population mean. The sample is obtained from a simple random sample or from a randomized experiment. And the sample has no outliers, and the population from which the sample is drawn is normally distributed. Or the sample size n is large. The sample values are independent of each other, and the sample size is less than 5% of the population size. So, step 1, we'll determine the null and alternative hypothesis. The hypothesis can be structured in one of 3 ways. Select a level of significance, we'll call it alpha, depending on the seriousness of making a type 1 error. And then compute the test statistic given by this formula. Look at that standard error there. You're going to be subtracting the mean from the population mean divided by S over root n. And this is coming from the student's t-distribution with n-1 degrees of freedom. So you'll utilize table 7 or inverse t on the calculator to get the critical value. And then finally, you'll state your conclusion there. All right, now, there's also technology available, and then we call this the p-value approach, where you're comparing the p-value to the alpha. So if the p-value is less than alpha, we will reject the null and accept the alternative. All right, we will say that there is sufficient evidence to reject the null and accept the alternative. And then step 5, you'll state your conclusion there, okay? So notice that the procedure just presented requires either the population from which the sample is drawn to be normal or the sample size to be large. The procedure is robust, so minor departures from normality will not adversely affect the results of the test. However, if the data includes outliers, the procedure should not be used. So here we have a problem. The mean height of American males is 176.3 centimeters. The height of the 44 male U.S. president, Washington through Trump, have a mean of 180.1 centimeters and a standard deviation of 7.1. Treating the 44 presidents as a simple random sample, determine if there is evidence to suggest that the U.S. presidents are taller than the typical American male. So use the alpha 0.05 level of significance. And I think that the key is that we're assuming that presidents are a simple random sample of all American males, and we actually know that it's not the case at all. But it's okay. We're going to carry on with this. We are going to identify our null and alternatives. The level of significance is alpha set to 0.05. And we are now going to identify the mean and standard deviation. And we calculate our test statistic of 3.55, which is pretty far away from the mean of 0. So we're talking about a p-value less than 0.001. It will definitely be less than 0.05. So we are definitely going to reject the null and accept the alternative. There is sufficient evidence at the 0.05 level and also at the 0.01 level to conclude that the US presidents are taller than the typical American male. There's another type of problem. All right, so the fun size of Snicker bars is supposed to weigh 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so that the mean weight is 20.1 grams. The quality control engineer at M&M Mars is concerned about the calibration. He obtains a random sample of 11 candy bars, weighs them, and obtains the data shown in Table 1. Should the machine be shut down and calibrated? Because shutting down the plant is very expensive, he decides to conduct the test at the 0.01 level of significance. All right, let's test for normality. Yeah, this is good. Also, well, from the box plot there, it doesn't look that normal, but approximately. We may proceed. Step 1. The engineer wishes to determine whether the Snickers has a mean weight of 20.1 or not. So we are going to set up a two-tailed test. The level of significance is 0.01. From the data, we can calculate the mean and standard deviation. The test statistic is here. And this is what we're getting. And it's because T naught, the 1.04, did not fall in that region. So we're not comparing the p-value this time. We're just basically comparing T naught. T naught needs to be in this region in order for us to reject. And it was not. So we will say that there is not sufficient evidence to conclude that the Snickers have a mean weight different from 20.1. The machine should not be shut down. Keep in mind, it still may not be, but we just don't have enough evidence at this time. If we were to do this out by hand, convert everything to the z-scores here, we would get -1 and 1 is like critical values, and the p-value is here. The p-value is actually still more. The p-value is between 0.4 and 0.3. We needed our p-value to be less than 0.05. A lot of different ways to do that problem. Let's move on. Keep in mind our own technology could have been used as well. Our calculator could have been used to conduct a hypothesis test. Let's review that really fast. Let's go to second, actually not second, just stat and then test. And we're going to go to a one, actually, it's just going to be a t-test here, isn't it? And we know the stats. All right. And we're going to set our 20.1, we said. Let's make sure we got our data right here. Let's go back a little bit. Our mean is 20.30. So we're going to set that up there. 20.301. Our standard deviation is 0.64. All right, looks like they want to know n for whatever reason. N was 11. An alternative is not equal to. All right. Now we're going to hit calc. Okay. So what did we get? Looks like we got our t to be 1.04. And that was what we got there, yeah. Our p is 0.322. And that's all. We're either going to compare our t with the critical region, the critical t values, or we're going to compare our p value to the alpha. Either one we compare, we see that our results are not that significant. Our sample, it wasn't much of a difference to reject the null. All right. Let's look at the next objective now, objective 2, understanding the difference between statistical significance and practical significance. So practical significance here is, it refers to the idea that while small differences between statistics and parameters stated in the null and are statistically significant, the difference may not be large enough to cause concern or be considered important. All right, so here we have a problem, and our alpha is 0.05. We're going to calculate our test statistic, and we get 1.64. And if we were to compare the p-values, we see that the p-value is less than 0.05. So we're going to reject the null. And we're going to say that while the difference between 29 and 29.3 is statistically significant, it has no practical meaning after all. 0.3 or 18 seconds really is not going to make anyone feel better about his or her commute to work. So here, large sample sizes can lead to statistically significant results, while the difference between the statistic and the parameter is not enough to be considered practically significant. And it's going to be the kind of t-test where we know what the stats are. So mean is 20. X bar is 18.2. Standard deviation 4.2. N looks like the size is 18. That's important to know. And alternative is less than 20, so that's fine. Enter. All right, looks like our p-value is 0.0433. Our test statistic is negative 1.82. It is a left tail test, so that's C. We knew it was left tail because the alternative H1 is mu is less than 20. So our p-value is between 0.025 and 0.05. All right, so it looks like our p-value is actually less than alpha, so we will reject because the p-value is less than alpha. All right, and it looks like all the other problems are very similar to that one. A lot of different types of hypothesis testing. It's kind of a lot to sift through and read through. Yeah, some of this might be a bit much, but nonetheless, we're here. We're here for you. If you have questions and videos that you want to talk about, let me know, and we'll get those ready.